Two machines, built nearly 50 years ago, are still talking to us from a place no human eye will ever see. The mission they were assigned was supposed to last only 5 years. Instead, the hardware has been running for 10 times that long. Both probes were assembled when calculators were still a luxury and home computers barely existed. The people who designed them are mostly retired. Many are gone. The machines themselves keep going. Voyager 1 sits roughly 15.8 billion miles from Earth. A radio signal traveling at the speed of light takes nearly 24 hours to reach it. Any message we send will not arrive until the next day. Any reply will arrive the day after that. The conversation we are still having with these probes happens across an entire day of silence in each direction. So, how is a 50-year-old machine, designed when home computers barely existed, still answering us across a void that wide? That is one of the strangest engineering stories of the last century, and most of it has never been told outside of JPL. And the further they drift, the stranger this story becomes, because what these two old machines have shown us along the way about the planets, about the boundary of our own solar system, about the fragility of the place we call home, is not the kind of thing you would expect from technology older than most of the people watching this video. The Voyagers did not just explore the outer solar system, they quietly rewrote it. And the discovery that may turn out to be the most important is the one that is still arriving, decades after anyone thought there would be anything left to find. Every great voyage starts with a door that is only open for a moment. In the case of the Voyagers, that door was a rare alignment of the 4 outer planets. In the mid-1960s, a young Caltech engineer doing routine trajectory calculations for NASA noticed something nobody else had spotted. Gary Flandreau realized that in the late 70s, the 4 outer planets of the solar system would briefly line up along the same side of the Sun, in a pattern that only repeats once every century and 3/4 or so. With that alignment in place, a single probe could ride the gravity of each giant world, in turn slinging itself from one to the next without burning extra fuel. Flandreau's mission concept got a romantic name: the Grand Tour. There was a catch. The configuration would open in the late 1970s and slam shut a few years later. Missed the window, and the next chance was 176 years away. Nobody alive on the planet would see it. Their great-grandchildren would not see it either. Congress did not love the price tag. The full multi-planet itinerary was killed in committee. What got funded instead was a stripped-down 2-planet 5-year version. Visit Jupiter and Saturn, then the mission ends. Anything beyond that you could extend if the hardware was still alive. They were not promising it would be. This is where the story quietly turns. The engineers at the Jet Propulsion Laboratory did not really build a 5-year mission. Not where it counted. They built the redundancy of a 40-year mission and labeled it 5 years to keep the budget through. Spare thrusters left dormant in case anything else failed. Power sources that would decay over decades instead of years. Backup computers waiting in silence. Heaters that did not need to switch on for 30 years. It was a kind of stubborn engineering optimism, dressed up in the language of caution. Was it allowed? Technically, yes. Was it expected? Absolutely not. Most planetary missions in the 70s built to the spec they were paid for and nothing more. The Voyager team did something different, and they did it quietly enough that nobody noticed at the time. Voyager 2 launched first on August 20th, 1977 from Cape Canaveral. Voyager 1 followed 16 days later on a faster trajectory that would overtake its twin before the year was out. They flew into the sky carrying 5-year rated technology, built by people who quietly suspected it might run for 50. To understand what the Voyagers have actually pulled off, you have to look at what they are made of, because the gap between the hardware on board and the things it has done is one of the strangest engineering stories ever told. Each probe is powered by a small nuclear battery. Not nuclear in the explosive sense. It is a device that converts the heat from decaying plutonium-238 into electricity, called a radioisotope thermoelectric generator. At launch, each one produced about 157 watts of electrical power. That is roughly enough to run 2 old-fashioned incandescent light bulbs. The half-life of plutonium-238 sits at just under 88 years, which is the key engineering detail of the whole mission. It means the power supply does not collapse. It just gradually thins, decade by decade, slowly enough that the essential instruments can't keep operating much longer than anyone expected. For pointing and steering, each probe carries 16 tiny thruster jets, 8 primary, 8 backup. The backups were never meant to do real work. They were just insurance. Insurance that nobody expected to ever cash in. Then in 2017, the primary thrusters in Voyager 1 started to degrade. Tiny pulses of gas were taking longer to fire than they used to. The probe was struggling to hold its antenna pointed at Earth. Engineers at JPL faced a problem with no good answer. The primary thrusters were wearing out. There was no way to send a repair crew, but sitting unused on the back of the spacecraft were the original backup jets, dormant since the flyby of Saturn in 1980. 37 years of total silence, frozen in the cold of interstellar travel for almost 4 decades. On November 28, 2017, the team uploaded a command across billions of miles, telling those thrusters to fire for the first time since most of the people running the test had been children. Then they waited. The round-trip signal time at that point was about 19.5 hours. They had to wait through a working day, a sleep, and most of another working day before the answer came back. The thrusters had fired perfectly, every one of them, as though no time had passed at all. That single decision extended the life of the mission by years. There's one more story about these machines that is hard to believe even when you have the documentation in front of you. In 2022, ground controllers noticed that the navigation data coming back from Voyager 1 had started to look like nonsense. Garbled, scrambled, internally inconsistent. The probe was not in distress. It was still flying correctly, but the data it was sending about its own attitude had stopped making sense. The team spent months working the problem with the patience of archaeologists. Eventually, they realized what had happened. Decades of cosmic radiation had subtly damaged one of the computers, and the probe had quietly started routing its navigation data through an older, failing backup unit instead of the correct one. The fix turned out to be embarrassingly simple. They told it to stop. It listened. The data came back clean. The spacecraft built before the Apple II had silently solved its own problem with the wrong tool, and then accepted being corrected from 15 billion miles away. Try to picture a piece of consumer electronics from that era doing the same thing. You can't, because no such piece exists. The onboard computers, meanwhile, are, by modern standards, almost charmingly primitive. Each Voyager has less processing power than a basic digital watch. Data is written onto 8-track magnetic tape, a recording technology already going out of fashion when the probes launched. Each spacecraft carries a dish antenna a little under 12 feet across. And somehow, with this ancient hardware, both probes have survived the asteroid belt, the radiation of Jupiter, temperature swings well over 200 degrees, and 5 decades in deep space. Not because the design was sophisticated, because it was tough. But none of this hardware survival would matter if the Voyagers had not seen anything worth surviving for. They had. Almost from the moment Voyager 1 arrived at Jupiter, the old textbooks started falling apart. And what came next, world after world, kept tearing them up. By the time it was over, the inner solar system would feel like a small, quiet place, and the outer planets would feel like 4 entirely separate alien wars. Voyager 1 reached Jupiter on March 5, 1979, after crossing more than 400 million miles in just 18 months. The atmosphere was supposed to be tidy. Scientists expected calm horizontal stripes of wind alternating in opposite directions. What the probe sent back instead was straight-up atmospheric violence. Storms wider than entire countries, columns of cloud material spiraling up and out in shapes no model had ever produced. The Great Red Spot, long suspected to be a rotating storm, turned out to be a counterclockwise hurricane bigger than the entire Earth, ringed by smaller storms that no telescope on the ground had ever seen. The neat, banded Jupiter of textbooks did not exist. The real Jupiter was a planet at war with itself permanently. Voyager also caught a faint set of rings around Jupiter, nothing like Saturn's bright system, but real, made of fine dust, invisible from Earth, only there because the probe was close enough to see them. And Voyager 1 did not just photograph Jupiter from a polite distance. It drove past several of the moons, and what it saw on the inner moon, Io, broke the textbooks even harder than the planet had. Io is supposed to be a quiet, airless rock. What Voyager photographed was a world covered in active volcanoes, spraying sulfur compounds hundreds of miles into space. The discovery of volcanism on another world for the first time outside Earth came out of a single image taken in passing by a navigation engineer who happened to notice an unusual plume on the limb of the moon. That image alone rewrote the field of comparative planetology. Months later, Voyager 1 swung past Saturn and gave us our first proper look at the planet that had been the symbol of the solar system since Galileo. The rings, it turned out, were not solid, not even a few large bands, but thousands of individual ringlets with gaps and ripples and tiny shepherding moons holding the structure in place. Strange braided patterns appeared in some of them, structures that should not have been physically stable but were. Saturn's largest moon, Titan, hidden under a thick orange haze, had an atmosphere denser than Earth's, dominated by nitrogen, with traces of methane and other complex molecules. A frozen world with weather of its own. Voyager 1 had to choose between continuing to the next planets or making a close pass to Titan. The team chose Titan because nothing else like it had ever been studied. The cost was that Voyager 1 was bent out of the ecliptic plane and could not go on to Uranus or Neptune. It became the price of one of the most consequential single observations of the mission. Voyager 2, traveling its longer path, did something even more improbable. It kept going. In January 1986, it arrived at Uranus, a planet so quietly strange that it had barely been studied at all. Uranus rotates on its side, tilted nearly 90 degrees, so that one pole faces the sun for decades, while the other sits in a 42-year night. Its magnetic field, Voyager discovered, is tilted at a wild 59 degrees relative to its axis, meaning the magnetic poles wobble and tumble through space as the planet turns. 10 new moons, 2 additional rings of dark dust, a magnetosphere so off-kilter that scientists still struggle to model it. And then Neptune. On August 25, 1989, 12 years after launch, Voyager 2 passed about 3,400 miles above Neptune's North Pole, the closest planetary flyby of the entire mission. Neptune greeted it with winds of roughly 1,500 miles per hour, the fastest ever measured anywhere in the solar system. A huge counter-rotating storm, the Great Dark Spot, dominated the southern hemisphere. 6 new moons, faint dark rings that turned out to be incomplete, partial arcs of debris that physicists said should not have stayed in place. They had stayed in place anyway. And then there was Triton. Voyager 2 swung past Neptune's largest moon and found something nobody had remotely expected. Triton orbits Neptune backwards, the only large moon in the solar system to do so, which is the smoking gun of a moon that did not form there but was captured from elsewhere. Its surface temperature is around minus 391 degrees Fahrenheit, among the coldest places ever measured anywhere. And from that frozen surface, geysers of nitrogen were spraying upward for almost 5 miles. An ice moon, captured by accident in the most violent corner of the outer solar system, somehow still geologically active. The Triton encounter closed the only complete reconnaissance of the 4 giant planets ever performed by one machine. Nothing else has ever attempted it. No future mission has yet been approved to try. By early 1990, Voyager 1 was about 3.7 billion miles from Earth, and NASA was about to switch off its cameras. The decision was practical. The cameras drew power that other instruments would need to study interstellar space. There were no more planets ahead to photograph. The mission scientists agreed. The cameras would go dark. Carl Sagan asked for one last image. He had been pushing the idea for years. Turn the camera around, aim it back at home, show humanity what it looked like from the furthest place a human machine had ever been. NASA agreed. On February 14, 1990, Voyager 1 rotated, pointed its lens toward the inner solar system, and pressed the shutter. In the picture that came back, Earth is less than a tenth of a pixel wide. A single point of pale blue light, caught inside a sunbeam of refracted color, almost lost. Trying to actually feel the scale of that for a second. every war fought, every song ever sung, every person who had ever lived or died fits inside that one dot. Carl Sagan wrote later that the image was a reminder of how small we are and of our responsibility to be kinder to each other and to the only home we have ever known. Then the cameras were switched off. They are still dark to this day. We'll never see Earth from that distance again. Not until something else, built by someone else, goes back out there and turns around and looks. After the cameras went dark, the Voyagers entered the part of their mission no one had ever truly believed would happen. They were going to try to leave the solar system, not in the easy sense of crossing the orbit of Pluto. That had already happened. In the hard sense of crossing the boundary where the sun stops being the dominant force in space. Our sun blows a constant wind of charged particles outward in every direction. That wind inflates a giant bubble around the entire solar system called the heliosphere. And the edge of that bubble, where the solar wind finally loses to the pressure of interstellar gas, is called the heliopause. On August 25, 2012, Voyager 1 crossed it. The probe registered a sharp drop in solar particles and a sharp rise in galactic cosmic rays, exactly as the models had predicted. It became the first human object ever to enter interstellar space. Then something the models did not predict happened. The magnetic field, which was supposed to change orientation past the heliopause to reflect the influence of nearby stars, did not change. It just kept pointing the way the sun's field had been pointing. NASA sat on the data for nearly a year, double-checking, trying to understand. When Voyager 2 crossed the same boundary 6 years later in 2018, it saw the same thing. No flip, no clean break, just a strange, magnetically tangled region the textbooks had never drawn correctly. The surprises did not stop at the magnetic field. Before crossing the heliopause, both probes wandered through the heliosheath, the thick, turbulent layer where the solar wind slows down and piles up against the interstellar medium. In that layer, the Voyagers found something the models had simply never imagined. Enormous magnetic bubbles, each roughly 100 million miles across, drifting like a kind of foam at the edge of the sun's bubble. No simulation, no theoretical paper, no orbital model had described them in advance. They behave like a giant pile of soap suds, and they may be one of the main mechanisms by which the heliosphere protects the inner solar system from incoming galactic cosmic rays. Without those probes drifting through, we might still be drawing the edge of our own sun's territory the wrong way. That is one of the discoveries still unfolding. The edge of our own bubble in the galaxy turns out to be far more irregular and turbulent than anyone modeled, possibly shaped by the death of a star that exploded billions of years ago and left our corner of the Milky Way the way we found it. Every answer the Voyagers sent back arrives bundled with new questions. Where do those magnetic bubbles come from? Why is the heliopause asymmetric? What was the supernova that carved this region of space, and how close did it come to destroying the world that would eventually give birth to us? The probes themselves cannot answer any of these. They can only keep noticing things and beaming the data back through a signal that gets weaker every year. Now the machines are fading, both of them. Voyager 1's primary engineering subsystems are slowly being switched off, one by one, to save power. Engineers debate the trade-offs the way doctors debate end-of-life care. Each instrument retired buys a little more time for the ones that remain. Each command sent has to wait nearly a full day to even arrive. Eventually, the power will drop too low to run any instrument at all, and the last transmission will arrive on Earth, and no more will follow. The end is coming. It may be only a few years away. It may be a little longer. Nobody's quite sure. Yet before that ending arrives, there is one more milestone still ahead. Voyager 1 is closing in on a distance no human-made object has ever reached. A full light day. The point at which a radio signal from Earth, traveling at the speed of light, takes a full 24 hours to arrive. We are weeks or months away from crossing that line. It is a symbolic threshold more than a physical one, but it is staggering. The probe will become the first object made by a species on a planet to drift far enough that even light needs an entire day to catch it. And after the transmission stops, the probes will keep moving. There's no destination, no remaining plan, nothing left to aim at. The Voyagers are simply going. In about 40,000 years, Voyager 1 will pass within a couple of light years of a small star in the constellation Camelopardalis. Voyager 2 will drift past another faint star called Ross 248. In roughly 296,000 years, Voyager 2 will glide past Sirius, the brightest point of light we see when we look up at night. Centuries after the last whisper has reached Earth, generations after the people who built these probes are gone, even when our own sun has begun to swell into the red star that will eventually swallow the inner planets, those two machines will still be drifting, carrying their golden records intact, more or less unchanged, through the void. It is worth pausing on those records for a moment. Each Voyager carries a gold-plated copper disc, slipped inside an aluminum jacket etched with instructions intended for whoever or whatever might one day find one of them. The records hold 90 minutes of music chosen from across the world, the sounds of thunder and wails and laughter and a human heartbeat, greetings in 55 languages, and 115 encoded images of life on this planet. The chance that any intelligence will ever recover them is statistically tiny. The chance that the discs themselves will outlast our species, our planet, and our star is almost certain. They will probably still be intact, drifting somewhere in this galaxy billions of years after the Earth itself is gone. A message in a bottle thrown into a cosmic ocean we cannot yet imagine the size of by people who knew it would never come back. Sit with what that actually means for a second. In 1977, a small group of people sat down and built something to operate in places they could not visit, last through timescales they could not plan around, and cross distances their own instruments could not yet measure. The redundancy went into every subsystem. A power source was chosen specifically because it would lose strength slowly enough to outrun the people working on it. Code was written for processors that would one day be older than anything else still running anywhere on the planet. 2 probes were pointed at a narrow slice of sky and let go. And as you watch this video, both of those probes are still out there, still sending, still doing, in the truest meaning of that word, what they were sent to do. If the idea of 2 old machines still pushing into the dark moves you, there is a question waiting on the other side of this video. The Voyagers got out only because the planets briefly lined up to throw them. That alignment is now gone. It will not come back in our lifetime. So how do we ever build a faster probe? One that does not need the gas giants to slingshot it. One that could reach interstellar space in a fraction of the time the Voyagers took. There is a kind of engine that could do exactly that, and it's not chemical or nuclear. Watch what's on your screen now to find out.